This is the second video for Chapter 36, Geometric Optics, and we're going to start by looking at a refracting surface. In this case, our second index of refraction of the material is going to be greater than our index of the first, and most likely our first index might be air. So we're going to go from an object, encounter this surface, and we're going to say that this surface has a radius of curvature equal to r. With a little bit of geometry, we can prove that the magnification of our image in relation to our object, the image height, h prime, over the object height, h, will be equal to negative index 1 over index 2 times the image distance over the object distance. And the q in this case will be positive, and the object distance p will also be positive because the object is on the side of the incoming rays, is originating the rays, and q is on the side of the outgoing rays. So, also we can also prove for this interface with a little bit of algebra and geometry that index 1, where we're originating, over the object distance p plus index 2, n2, over the image distance q is equal to n2 minus n1 over the radius of curvature for this interface. So these are two neat little equations for this refracting surface. Real images will actually be formed on the side opposite from the object, and so the actual rays are forming the image, hence it is a real image. Let's take these newfound formulas to the absolute extreme. Let's take a look at a flat refracting surface, and we're going to apply these formulas, and they should work. In this case, our first index is actually greater than our second index, and our radius of curvature of the interface is actually going to be infinity, because if you have a radius of curvature and you start increasing that radius of curvature, your curvature is going to start going flatter and flatter as r gets larger and larger. Looking at this, as the rays are coming in, if we were to draw a normal to this interface surface, we would find that our angle of incidence is going to be smaller than our angle of refraction. We're going to refract away from the normal. So the rays are going to diverge as they're going through this interface, and they're going to appear to come from some point that's inside the first material. So that would be the location of our image, is actually inside the first material. The image will be virtual because our image distance will be negative. The image is not on the side of the outgoing rays. The outgoing rays are on the other, or the N2 side of the interface, and the image is on the first side. So it's not on the side of the outgoing rays, hence the image distance is negative, and that makes the image a virtual image. And since for a flat surface we have a radius of curvature that is infinitely large, if we apply our formula here, 1 over the radius of curvature will be infinity. It will be 0. 1 over infinity will be 0. And then with the solve for our image distance, q, we have q is equal to a negative index 2 over index 1 times the object distance p. Object distance p is positive. n2 is a number that's smaller than n1 because we're going from a higher index to a lower index. So our image, at least the magnitude of our image distance, is going to be less than our object distance, and it's going to be on the same side as the object. So if we're looking at this, the image is going to appear closer to the interface than the actual object is. Let's try this out with an example. A small fish is swimming at a depth d below the surface of a pond. What is the apparent depth of the fish as viewed from directly overhead? So we have the fish, which is originating the rays of light from the fish, and they're coming over from the water, hitting the interface with the air, and then refracting away from the normal. And so the image of that fish is going to appear like it's shallower in the water. That image distance will be equal to negative n2 over n1. n1 is the index of the water. n2 is the index of the air, because, again, the rays are originating from the fish inside the water. So that's going to be equal to a negative index of air 1 over 1.33 times our object distance d, which would be a negative 0.75 d. Negative meaning that we're on the same side as the originating object, and so we have a virtual image, and it's 3/4 of the actual object distance. So if you're looking at this fish in the water, the fish is going to appear like it's 25% closer to the surface of the water than it actually is. And so if you try to reach down to try to grab the fish, you're very likely to miss it. It's going to be reversed for the fish looking up. For you, being the object originating the light rays, they're going to refract inward, and to the fish, you're going to actually appear like you're further away than you actually are, about 33% further away than you actually are. Fish are probably used to that, and because they're not going to see anything other than that situation, but you are going to appear further away than you actually are. Let's go scuba diving. Objects viewed underwater with a naked eye appear blurred and out of focus. A scuba diver, using a mask, however, has a clear view of underwater objects. Explain how this might work. Let's say you're swimming underwater and you're not wearing a mask, and you see this manatee coming towards you, and manatees are very gentle creatures, and so you kind of rejoice in the fact that you can share this water with such a serene and enjoyable creature as a manatee. However, you're not seeing things clearly because your eyes are designed to deal with an air environment. So the optics of your eyes are dealing with an index of refraction around you of the general environment of 1 going into the fluid of your eyes. The reality, though, is if you're swimming in water, all of a sudden the air has been replaced by index of refraction of water, and things will appear blurred to you, unless you wear a mask. If you wear a mask, then you have a layer of air right before your eyes, and hence the optics of your eyes work as they should with that layer of air before going into your eyes. So instead of seeing a blurred image, what you thought was a manatee, you might actually see the reality that it was actually Bruce the shark, and he looks pretty hungry. Fortunately, he's only chasing after fish in this particular instance. Sunsets. Light rays from the sun are bent as they pass into the Earth's atmosphere. Earth has a layer of atmosphere, and the light rays get bent. So it's a gradual bend because the light passes through these layers of the atmosphere, but as it's sunset, there's more atmosphere for it to go through from that angle to your eyes, as opposed to the sun being high in the sky during the day. So there's going to be more refraction occurring near a sunset or a sunrise. The light is bent in such a way that it's going to appear, the sun's going to appear coming from a different direction. The sun could actually be below the horizon, already set, and you'll still see the image of the sun because the light from below the horizon has bent and made it to your eyes. So the sunset could have occurred before you actually stop seeing the sun. A similar type of refractive event is the mirage. Because the air is hotter near the surface of the ground, there will be a different index of refraction for the heated air. And if we're looking at this situation where you're looking at a tree, say you're in this Jeep, you would see a direct image coming directly from the tree, this ray A hitting your eyes, and then the ray that was directed not towards you, but maybe towards the ground, might actually bend due to the heated air near the ground as opposed to cooler up above, and hence that refraction might bend that light rays and that might actually make it to your eyes as well. So you're going to see a second image of the same tree. The second image will actually be inverted. And so you'll see two images, one the direct image and one the inverted image of the light that has been bent because of the heated ground. Here's a mirage. It's particularly cruel if you happen to be in a desert and you're thirsty, and the mirage makes it look like there's a lake of water there that is reflecting the image off the water, and so you're seeing the reflection that way. But that's not the case. You're seeing the bent image coming back to you because the surface of the ground is so hot and actually bending those rays. So actually there is no water there, and you're about to find that out once you venture into that area. A superior image could happen the same way. Say the air up above is hotter than the air closer to the water in this case. And so if you had an iceberg on the water, that image might be going, one image is coming directly towards you, but another image might be going away from you, but because of the heated air, it's bent towards you, and so you see a secondary image of the same object. And that secondary image is this iceberg that appears to be floating in the air. It's either an iceberg floating in the air due to a mirage, or it could be an actual UFO. So, I don't know. Time will tell. Thin lenses. A lens consists of a piece of glass or plastic. Each of its two refracting surfaces is either a sphere or a plane, or both, or one or the other. Lenses are commonly referred to used to form images by refraction in optical instruments. A thin lens is one in which the distance between the surface of the lens and the center of the lens is negligible. Let's take a look at a converging thin lens. We have a biconvex, which is two convex surfaces. We have a convex and a concave. You have to look at each of them from the outside in. So a convex and then the concave lens. And then this one would be a convex plane, or you could say it's plano-convex. Converging lenses will have positive focal lengths, and they are all thickest in the middle. So one way you could identify a converging lens with a positive focal length is that it's always thicker in the middle than it is on the edge. And all three of these are converging lenses because they're thicker in the middle than they are on the ends. As opposed to a diverging lens, which has a negative focal length, so the image will not be located on the side of the outgoing rays, and they are thickest at the edges. So they're thinner in between. So just looking at the lens, you see that if the middle is thinner than the outer edges, it is a diverging lens, and all three of these are diverging. So we have biconcave, a convex, and a concave, but it's thicker on the outside, so it is a diverging lens, and a plano-concave lens. Sign conventions for lenses. The object distance P is always positive if it is on the same side as the incoming light, negative if it's not. The image distance Q is always positive if it's on the same side as the outgoing light, negative if it's not. And I've seen these in the book, I've seen it in many books, where they try to confuse us and give you big tables, one for lenses, one for mirrors, and if this is this and this is that. But if you keep this straight, it's very simple. It's the same thing for mirrors as it is for lenses. If you're on the same side as the incoming light, then your object distance is positive, negative if it's not. And if you're on the same side as the outgoing light, either mirrors, lenses, or refractive surfaces, if you're on the same side as the outgoing light, your image distance is positive, negative if you're not. It's as simple as that. These are the same for mirrors. The focal length. designated by little f, is the image distance that corresponds to an infinite object distance. A thin lens will have two focal points corresponding to parallel rays from the left. Parallel rays coming into the lens will converge on a point, and that distance from the lens to that point is the focal length. And parallel rays from the right. Take the same lens, have parallel rays hit the lens from the right, converge to the point, and that will be the focal length, and it's the same focal length. But if you have parallel rays encountering a diverging lens, the rays going out will diverge, and it will appear to come from a point, and that distance from that point to the lens, or to the center of this thin lens, would be the focal length. So parallel rays diverge after passing through a diverging lens. The focal point is a point where the rays appear to have originated from either side. The focal length of a lens is given by the Lensmaker equation, and it looks like this. 1 over the focal length is equal to the index of refraction of the material of the lens, n, minus 1, times 1 over the first radius encountered by the light, minus 1 over the second radius encountered by the light for the lens. So radius 1 and radius 2 are positive if the center of curvature is on the outgoing side of the lens. So you're going to have to imagine light coming from one way or the other. But once you determine which side the light is coming from, encountering the lens, then you define your radius of curvature based on that. And if the center of curvature is on the outgoing side of the light, then it is a positive center of curvature and a positive radius. Negative if the center of curvature is on the incoming side of the light. So if the light were coming into a concave side, then you would treat that radius as being negative. Like an image in relation to real rays exiting. If the lens is immersed in a fluid other than, say, air, this n value is interpreted not as the index of refraction of the material of the lens, but the ratio of the index of the material to the index of refraction for the fluid. Now, if the fluid were air, which is 1, is the index of the material over 1. Now, if the fluid were water, 1.33, it would be the index of refraction of the material, say glass, 1.5 over 1.33, and that would reduce the value of this n by the value of the fluid that you've immersed the lens into. Here's an example of this Lensmaker equation, and it's from your problem set. A plane convex lens is made of glass, index refraction 1.5, with one flat surface and the other having a radius of 20 centimeters. What is the focal length in centimeters of this lens? Alright, so we got this lens. It's plano convex, and it is a converging lens because it's thicker in the middle than it is on the outside, so we should expect a positive focal length. Now we have to assume the light coming from one way or the other. So in this case we're going to come from the left and exit on the right. So we're going to assume our ray direction. And as this light is encountering the first surface, we find that first surface is the plane, and that should be a radius of curvature of infinity for a plane. So our first radius is going to be R1 equal to infinity. And then it's going to encounter the second surface, and it's curved in a concave way in relation to the direction that the ray is coming in, and hence the center of curvature is not on the side of the outgoing ray. So our radius for the second surface is actually a negative 20 centimeters. We're going to use this in our lens equation, Lensmaker equation. 1 over the focal length is equal to the index of refraction of the glass, 1.5 minus 1. 1 over the first radius, infinity, minus 1 over the second radius, negative 20. We have a minus minus for this second fraction, which will be plus, and 1 over infinity will be 0. So we're going to have 0.5 times a positive 1 over 20, which is going to give us 1 over 40. And then if we flip both sides, then our focal length would be 40 centimeters. Positive. So the focal length of this thin lens, this by the Lensmaker equation, is 40 centimeters. Just curious, what would happen if you had approached this lens in the opposite way? It's still the same lens, but we're just going to have the rays come from the left and go to the right again, but we just turn the lens around, and now we're going to encounter the convex surface first and then the plane. Our first radius then is going to have a center of curvature on the outgoing side of the rays of light. So our first radius will be a positive 20. The second surface is going to be a plane, and hence that will have a radius of curvature of infinity. So in our Lensmaker equation, we're going to have 1.5 minus 1, 1 over the first radius, 20, positive 20, minus 1 over infinity, which is going to be 0. And again, we have 0.5 times 1 over 20, 1 over 40. Focal length is 40 centimeters, positive. Didn't matter. So we can apply this formula no matter which orientation we have for this lens, and if we use our convention correctly, then we will still come up with the right answer. It's good to know. We want to come up with some thin lens equations, and for that we're going to look at some geometry for the lens. Here we have an object of height h, and we have a couple of rays encountering this lens. First one's coming in parallel, so it's going to go through the focal point, and the second one's going to go right through the middle of the lens and continue onward, and where those two converge is where our image is. So we have our image over here, h prime, and it's inverted, as we expect. Let's look at some triangles here. From the first blue triangle here, with angle alpha, we can see that the tangent of alpha is the opposite side, h, over the object distance, p. And we're going to look at this gold triangle down over here, same angle alpha, and we can see that the tangent of alpha here will be a negative h as we're going in the negative y direction, over this distance here, which will be the image distance, q. Taking the ratio of these two, we get, with a slight manipulation, because we're going to have 1 is equal to the ratio of these two, we will get that the magnification is the image height over the object height, h prime over h, and that's equal to negative q over p. And in this particular case, p is positive because it's on the side of the incoming rays, and q is positive because it's on the side of the outgoing rays. So the magnification is negative, it's inverted, and that's what we expect. Also note from the same figure, if we're looking at angle theta, and look at this little triangle right here, from the focal point to the lens, and this distance from P to Q is actually equal to h, because this line here from 2 is parallel to the principal axis. So we have h here, so the tangent of theta is equal to h over the focal length f. And this angle over here is also theta for the similar triangle over here, and the tangent of theta will be equal to negative h over this distance right here, which will be the image distance minus the focal length f, q minus f. Take the ratio of these two, and we have the q minus f over f is equal to negative h prime over h, but we know from the magnification that h prime over h is equal to the negative q over p. So we have a negative negative here. Those negatives cancel out. And with a little bit of algebra manipulation, we'll go through these steps. You can verify them if you wish. We're just doing simple algebraic steps. Q divided by Q is going to cancel out here. P divided by P, cancel out. And voila, we have 1 over the object distance P plus 1 over the image distance Q is equal to 1 over the focal length. That is the thin lens equation and it's beautifully the same as our mirror equation. So we have two thin lens equations. We have 1 over P. Both of these are the same, exactly the same as the formulas we had for mirrors. Great. Our sign conventions are exactly the same. Object distance is positive, it's on the side of the incoming rays. Image distance is positive, it's on the side of the outgoing rays. Those conventions are exactly the same. The equations can be used for both converging and diverging lenses, noting that a converging lens will have a positive focal length and a diverging lens will have a negative focal length. So keep that in mind, though. If you read a problem and they talk about the lens and they say it's a diverging lens, when you put in your focal length for f, there'll be a negative value for f. Negative for a diverging lens, positive for a converging lens, and if you solve for those, that's what you should get as well. We're also going to look at ray diagrams for thin lenses. Ray 1 is drawn parallel to the first principal axis. It should pass through or appear to come from one of the focal lengths. Ray 2 is drawn through the center of the lens and passes straight through, continues in a straight line. Ray 3 is drawn from the other focal point and emerges from the lens parallel to the principal axis. We'll use these rays, 2 of them, to help us construct where the image is. Here's a converging lens with the object distance greater than the focal length f. So the object's out here. Here's our focal point, and we're further away from the lens than the focal point. Let's try this out. We've got a parallel ray coming in, and as it encounters the lens, a parallel ray will converge on the focal point on the other side. So there's one exiting ray on the other side. A ray that goes through the center of the lens will appear to continue all the way through. And where these two converge, these two rays, that should be the point of where the image is. So our image is located over here where the two rays converge. Excellent. So just 2 rays is all I need to locate this third point. But I could have had a ray go through this first focal point. As it encounters the lens, it's going to come out parallel, and that also goes through where the image is. This image will be real because it's actually comprised of the actual rays that are outgoing from the lens. And it's inverted. Our image distance is a positive quantity. Q is positive. P is a positive quantity. So our magnification will be a negative Q over P. Magnification is negative. Hence, the image is inverted. Here's a ray diagram for the object inside the focal point. So now we put the object, and the object distance is less than the focal length. We're going to try the same thing with our rays. We're going to have one ray come in parallel, and it's going to appear, or it's going to go and converge through the focal point on the other side. So that appears, if we draw it back, is coming from that direction, out back this way. We have another ray go right through the center of the lens and continue undeterred to the other side. Where these two rays appear to come from and converge, that's where our image should be. So we're going to draw them, trace them back, and there's the tip of our image. The image is actually going to be larger than the object, and it's going to be behind the lens. So it's not on the side of the outgoing rays. The image distance, hence, will be negative, and the magnification will be a positive quantity because a negative over a positive quantity. So the magnification is going to be upright, and it's going to be greater than the object. The image is going to be greater than the object. Here's a third ray. It appears to come from this focal point here. As it passes through here on its way to the lens, it comes out parallel. Image is virtual and upright. Finally, let's try a ray diagram for a diverging lens. Here's a diverging lens. We have a parallel ray coming in. It's going to diverge when it reaches the lens and appear, if it were parallel coming in, it's going to appear to have come from this focal point over here. So as we follow it backwards, it appears to come from that point. Let's try another ray. Right through the center of the lens, undeterred to the other side, and that appears to come directly from that point. So where those two converge, that's where our actual image is. We can see in this case the image is actually on the same side as the object, and it is smaller than the object itself. So the image distance is going to be negative, and it's going to be less in magnitude than Q is going to be less in magnitude than P, and hence our magnification is going to be less than 1, and it's going to be upright because we're going to have a positive magnification because our Q is a negative quantity. Here's a third ray. It's headed towards the other focal point, and when it encounters the diverging lens, it comes out parallel. And if we follow that back, that also will converge on our image. So any two of these three rays would help us locate where this image is. Image is virtual, image is upright. In this case, the image is smaller than the object. And that helps us with a ray diagram for a diverging lens. That concludes the second lecture in Geometric Optics, Chapter 36.